Problem number 15. Suppose an attractive nuclear force acts between two protons, which may be written as F equal to C e to the power of minus kr divided by r squared. So we have two protons inside the nucleus, and there is an attractive nuclear force because otherwise they would repel. There's an attractive nuclear force between the proton, and the force on each proton is given by C e to the power of minus kr divided by r squared. So in the first part of the question, we are required to find the dimensional formula and the appropriate SI unit for C and K. So we have to find the dimensional formula for C and K. Now, you know that this is an exponential number, e to the power of minus kr, and exponential numbers do not have any dimensions. So that means the dimensional formula for C divided by r squared has to be equal, if this equation is correct dimensionally, has to be equal to that of F. And from here we can find out the dimensional formula for C must then be equal to the dimensional formula for F times r squared. Now from this we could see the unit, the SI unit. We have to find the SI unit as well, the SI unit of C and K. The SI unit of C from this equation is simply Newton, because force has an SI unit of Newton, and this is distance, this is meter square. Newton meter square is the SI unit for C, and the dimensional formula is, this is m1 L1 T minus 2 times L square. So the dimensional formula is m1 L3 T minus 2. Okay. We also have to find out the dimensional formula and SI unit for K. So K minus K times R is a number. So that means K times R has no dimensions. That's only possible. R is the distance. That's only possible when K has the dimensions of inverse distance. And that is equal to 1 by L, or L to the power of minus 1. And its SI unit is, the SI unit is clearly meter inverse. Okay, so we have found the answer for the A part of this question. Let's look at the B part. Suppose that K equal to 1 Fermi inverse, and that the repulsive electric force between the protons is just balanced by the attractive nuclear force when the separation is 5 Fermi. So find the value of C. So here there's a attractive nuclear force acting, but there is also an electrostatic repulsive force in this direction. And when the protons are at a distance of 5 Fermi inside the nucleus, then the electrostatic force balances the nuclear force. So at 5 Fermi distance, and that is at r equal to 5 Fermi, the electrostatic force at this distance, the electrostatic force balances the nuclear force. And what is the electrostatic force? That is K times, that is 9 into 10 to the power of 9, times the charge of this proton and charge of this proton, product of the charges. So the charge of proton is 1.6 into 10 to the power of minus 19, same as that on electron. You just square this number, divided by distance squared. So this is your electrostatic force, and you got to equate it with the nuclear force, and that is given in the question itself. This is C times e to the power of minus k times r divided by r square. Okay, this r square cancels. Now here, look, we have e to the power of minus kr, and we know that this is equal to e to the power of k is given. It's equal to 1 Fermi inverse, so it's 1 by Fermi. Okay, and r is 5 Fermi. So 10 to the power of minus 15 Fermi cancels out. So we are left with e to the power of minus 5. Okay, this e is the irrational number. You know, its value is roughly 2.72. You take a power of minus 5 over it, and let's see what we get. Okay, so we have 2.72 raised to the power of minus 5. So we're getting 0.0067. So the e to the power of minus 5 is 0.0067. Okay. You substitute this e to the power of minus 5 over here and we'll get c. So c is nothing but 9 into 10 to the power of 9. And this is 1.6 square is 2.56 into 10 to the power of minus 38 whole divided by this e to the power of minus kr turns out to be 0.0067. This will go in the denominator, so this is 0.0067. We just have to find, and the unit for an SI system for C is Newton meter square. So let's solve this. So how much is this? So once we solve this, so this is 23.04 divided by 0.0067 times, this is 10 to the power of minus 9 minus 38 minus 29 Newton meter square. So let's solve this here in a calculator. So what number do we have? We have 23.04. You divide it by 0.0067. So what number are we getting? That's 3438.8. Let's take this number in scientific form. This is roughly 3.4 10 to the power of 3. So this is 3.4 10 to the power of 3. You equate that with 10 to the power of minus 29, and that is 10 to the power of minus 26 Newton meter square. This is your answer. Okay, let's look at the next question. Question 16. Here in this problem, we are given 3 charges. Each charge is 2 into 10 to the power of minus 6 Coulomb. Are held at 3 corners of an equilateral triangle of side 5 centimeters. Find the Coulomb force experienced by one of the charges due to the rest 2. So let us assume ABC is our equilateral triangle. And we have 3 equal charges. Let's consider for the moment that the charge has a magnitude Q. Now we want to calculate the Coulomb force experienced by one of the charge. Let us assume that charge is the charge at vertex A. And we have to calculate the Coulomb force due to the other 2, net force. So this one is going to repel it in this direction. This one is going to repel it in this direction. Since the distance is same, this force is simply KQ. Let's assume the side length of the equilateral triangle is L. So KQ squared divided by L squared. This force is also going to be equal to KQ square by L square. And the angle here is 60 degrees, so the angle between these 2 forces is 60 degrees. So if you assume this one to be F, this one to be F, then your net Coulomb force acting on the charge at vertex A is simply given by, this is 62 f square plus 2 times f and f cosine of the angle between them, and taking the square root of the whole thing, will end up with this thing, root 3 times f. I think we've already done it in the previous videos, how we come up with root 3 times f. So this is root 3 times f is k q square divided by L square. Let's substitute the values. Root 3 is 1.732 roughly. It's an irrational number. K we take as 9 into 10 to the power of 9. And the charge is given. Each charge has a magnitude 2.0 10 to the power of minus 6. So 2.0 into 10 to the power of minus 6. You take the square, and in the denominator you take the distance between any two charges, which is also given, that's 5 centimeters. So this is 5 into 10 to the power of minus 2. You square it, and you will get a force in newtons, because all the units that we've chosen are in SI system. So this is 1.732 times 9 times 4, 2 2s is 4, 9 4s is 36, so instead of 9 we'll write 36. Okay, in the denominator we'll get a 25 here, and let's put this separately, these numbers, the powers of 10, 10 to the 9, and this would be minus 12, and this would be plus 4. So this would be 13 minus 12, that is 10. So what number are we getting? Is you multiply that 10 with this is 17.32 times 36 divided by 25 newtons. So what is that? Let's see that in a calculator. So this is 17.32 times 36 divided by 25. And we're getting 24.94, so 24.9 newtons. Okay, in which direction are we getting this force, the net Coulomb force? You could see this. We also know that if the angle here is theta, then the resultant force will be theta by 2. That's at an angle of 30 degrees. So the net force acts at 30 degrees angle with respect to, you can take this side, BA produced. If you produce this BA side, it's making an angle of 30 degrees with respect to BA produced. Okay. Okay, let's look at the next problem. 4 equal charges, 2.0 10 to the minus 6 Coulomb, each are fixed at 4 corners of a square of side 5 centimeters. Find the Coulomb force experienced by one of the charges due to the rest 3. So let us assume the square ABCD, on the vertices of which we have equal charges, say Q. This one is Q, this one is Q, this one is Q, and this one is Q. And let the side length of a square be L. So we have to calculate the Coulomb force on one charge. Let us assume that charge is the charge at vertex C. So we have to calculate the total Coulomb force experienced by this charge here at point C. So this one here, okay, the charge at vertex D is going to exert a force in this direction, and that force would be K times the product of charges, that is Q squared, divided by the distance, that is L square. Similarly, charge at vertex B is going to exert a force on charge at vertex C in this direction, and that force is also going to be the same because the charges are same. So it would be K, the product of the charges, that is Q squared, divided by the distance squared, that is L squared. So this vertex we have taken care of, this vertex we have taken care of. These two forces will combine to give a resultant. If we use these two forces will combine to give a resultant in this direction. And since the angle between these two forces is 90 degrees, this one is 90 degrees, because the sides of a square are inclined at an angle 90 degrees each. So this is 90 degrees. So the resultant is going to be, if you call this F, this is also equal to F, and the angle is 90 degrees, the resultant force would be simply root 2 times F. And that is equal to root 2 times K Q square divided by L square. Okay, this is the resultant of these two forces. The forces exerted by charge at vertex D and charge at vertex B onto charge at vertex C. Now we have to take care of another, we have to consider another charge here, that's the charge at vertex A. This one is also going to exert a force of repulsion on this charge along the diagonal, which is at 45 degrees angle. That means that force is also going to act in the same direction as the resultant of these two forces. And what would be the magnitude of this force? The magnitude of this force is simply K Q square divided by the distance square. Now this distance is L, this is L, so the diagonal of a square is simply root 2 times L, and if you square this distance, this is nothing but 2L square. Okay, so these two vectors, we have to take the sum of these two vectors, that gives us the resultant force. So the net force is just the sum of this force, that's the resultant of this one and this one, which is equal to root 2 times K Q square divided by L square plus the force exerted by the charge at vertex A, and that we have found out is KQ square by 2L square. So a few things can come out common, that is KQ square by L square times root 2 plus 1 by 2. Okay, let's substitute the values. K is 9 into 10 to the 9, and the charge on each vertex is 2.010 to the minus 6. So 2.0 into 10 to the power of minus 6 whole squared divided by the distance square. What's the side length? That's 5 centimeters. That's 5 into 10 to the power of minus 2. You square it, and this is root 2. We can take 1.414. 1.41 plus you take a half, that is 0.5. So let's solve this. This is 9, this is 2 2s is 4, 9 4s is 36 into 10 to the power of 9. This is minus 12, and from the denominator we have a plus 4. Okay, divided by 5 square is 25, divided by 25. Okay, times what do we get inside the bracket? That is 1.91. Okay, so this is 36 by 25. Let's find out how much is that. 36 divided by 25. We're getting 1.44 times, this is this is 9 plus 4 is 13, minus 12 is 1, that's 10. Multiplied by 10, you get this number times 1.91. 1.91. So we get 27.5, so approximately it's 27.5 newtons. Okay, this is the net force acting on the charge at vertex C. And at what angle? So we already know that these two forces are equal, and this resultant is going to act along 45 degrees. So is the other force that's acting at the net force is in this at 45 degrees angle with respect to, you could write this force is acting at 45 degrees with respect to, take one side, say DC produced. Okay, I hope you understand this. Okay, let's look at the next problem. So problem number 18. A hydrogen atom contains one proton and an electron. It may be assumed that the electron revolves in a circle of radius 0.53 angstroms. 1 angstrom, of course, we know it's 10 to the power of minus 10 meters. Okay, we have a proton in a hydrogen atom inside the nucleus, and there is an electron revolving in a certain orbit of radius r, and this electron, this radius here is given as 0.53 angstroms, that is 10 to the power of minus 10 meters. The hydrogen atom is said to be in the ground state in this case. So what we have to find is the magnitude of the electrical force between the proton and an electron of the hydrogen atom. So this proton is going to attract electron with an electrostatic force. So we can calculate that force by simply using Coulomb's law, Q squared divided by R squared, because the charge is similar on this. So instead of K we write 9 to the power of 9. Q, the charge on a proton and an electron is similar, and that's 1.6, 10 to the power of minus 19. You take a square of this, divided by the distance square, that is 0.53 times 10 to the minus 10. You take a whole square of this number, this many newtons. So we'll solve this. 9 into this is 1.6 squared is 2.56 into 10 to the power of this is minus 38, and this is minus 29, divided by this would be 0.53 whole squared times 10 to the power of minus 20 newtons. So this is equal to, let's use a calculator to find out this number. So 9 into 2.56 is nothing but 23.04, and you divide this number by the square of 0.53. You take its square, what's the square? Okay, you take a square of this, and you are getting 82, approximately 82. This is 82 into 10 to the power of, this is minus 9 newtons. So, which is in scientific form, we could write this as 8.2 into 10 to the power of minus 8 newtons. This one was a very simple question. Okay, let's move quickly to the next question. This is our next question. Question 19. It says that find the speed of an electron in the ground state of a hydrogen atom. The description of ground state is given in the previous problem, of course. We have already found out the force acting on the electron in the ground state. So this force is acting towards the center. So this electrostatic force is providing the necessary centripetal force for the electron to move in a circle. So this electrostatic force provides the necessary speed for it to move in a circle. So let us equate that centripetal force with the electrostatic force. So the electrostatic force is providing the necessary centripetal force, that is mv squared divided by r. And we know that we have to calculate the speed here. This is k E squared divided by r squared is equal to mv squared divided by r. This r and r cancels out. So the expression for v is simply k E squared divided by m into r, and you take a square root of this number. Okay, because it's v squared here when it turns into this, and this simplifies into e root of k divided by m into r. So let's substitute the values. This is 1.6 into 10 to the power of minus 19, and inside we have 9 into 10 to the power of 9 divided by the mass of the electron, that is 9.1. Let's take approximately 9 into 10 to the power of minus 31 kg times the distance that we have, the radius of the orbit, the ground state orbit, that's 0.53 into 10 to the power of minus 10 meters. Now let's solve this. So what do we have here? The 9 and 9 goes here, and this is 10 raised to the power minus 31 minus 10, 10 raised to the power minus 41. When it goes upstairs, it becomes, you add plus 9 to it, then 10 raised to the power minus plus 41 plus 9, that's 10 raised to the power 50. And for 10 raised to the power 50, the square root is so you write 1.6 into 10 to the power of minus 19. The square root of 10 raised to the power 50 is 10 raised to the power of 25. Then you take a square root of only, you have to take a square root of only 0.53. So let us do that in a calculator and see what results we're getting. So we have 1.6. You divide by the square root of this number, just write 0.53, you take its square root, and the result is you're getting 2.19. This is 2.19 into 10 raised to the power 25 minus this 10 raised to the power of 6 meters per second. So this is the speed of the electron in the ground state of hydrogen atom in its orbit. Okay. In the next video, we are going to take some more questions or some more problems from this chapter. Thank you.